Okay, so welcome back, class. You don't realize, but I had a little break. So we talked about the memory layout, how stack grow, and then when they calling a subroutine, and then how they shrink back when they return. And we talked about the memory. So now let's move on to introduce a few more instructions. We have learned load a word and store word instruction, LW, SW. I remember one student who was asking, as we know, it's not just always word. Integer is a word, 4 bytes, but we have 16-bit integers. We have single characters, which is 1 byte. We could have loaded a word, and then we use, for example, we can use a logical operation AND. We can AND. What I was trying to say is something like this. We could use load T0. Let's say, I'm making it up. So we load a word there, and then we can do AND I T0 T0. For example, if we just 1 byte at that address, then we can just do FF. That will do 1 byte. Now that's not very efficient. It's 2 instructions, and also you're loading a lot of bytes that you don't use. It's very wasteful of the memory and energy. So MIPS has a byte and a half load and store. And just as you expected, it's LB stands for low byte, and you give an offset. And this base register is like a rolling word, and this is destination register. And also it's sign extended, meaning if the byte has, if you remember, sign extension means the most significant bit gets duplicated into the top part of the register. So if the F bit of this byte is 1, then all the top 24 bits become 1 in the RT. But if the top bit is 0, and then the top 24 bits in this, it became 0. The last 8 bits take the content from this byte at this address. There's also unsigned version of load LBU. In that case, top 24 bits are just filled with 0. Similarly, you can store a register into a particular address. In this case, you just store the rightmost 8 bits. Now this takes care of the byte. The half word is separate instructions. I don't think it's listed here. I can try to find out later. But anyway, there is an instruction reference web page. I strongly recommend everybody go there, find out everything you want. So I'm trying to find out. Okay, anyway, let's come back. I think there's some examples here. The example is str copy. This is copy a string to another string. In this case, it's copying a string y, or array of char, which is a string, to array of x. Now terminated means the last character is 0. I don't understand why this is naive there. Okay, we'll work it out later. So this code is, you take a variable called I, you set I to 0, and then what you're doing is, this looks a little bit complicated, but what I'm really doing is, this does 2 things in one. It will load the byte which is the ith element of y, assigning it to the x ith element in x array, and then check the value to see if it's equal to 0. If it's not equal to 0, I is incremented by 1, and continue to loop it again until you hit 0. So that's why now terminated means. Once you hit the 0, you break out. You're done with the copying, so you're fine. So in this, we assume x and y are in A0 and A1. That's because they're parameters passed in. And we use S0, which means you should store it in the stack because it's the register you should save. So let's see how it does it. First, you decrement the stack pointer by 4 so that it can store S0. So indeed, you store S0 to the newly allocated space. And then just clear S0 to be 0. Add a 0 to 0 equals 0. So what it's doing is set I to 0. And then we start to do the part. Let's see what they're doing. A1 is the base address of y. S0 is I. So you add these two together, that became the address of y I. And then you just do a load byte at that address. Offset is set to be 0. That means, you've got the exact address. You don't have to do the offset. So you just load that byte into T2. So T2 now has this value. And then he also does add A0 of S0. That became the address of X, the ith element in X array. So, and you put the result into T3, that's the address. And then it does this SB is the store byte. You store the last 8 bits in T2, which is the host content of Y, into that T3 address, which is X. By doing this, now X I sub I equals Y sub I. So now we start to check the content, whether it's 0 or not. So basically using B equal. If it's equal, it's going to jump. So compare this with 0. If it's 0, you jump to L2. It breaks the loop. Now, if it's not 0, that means you have not reached the end of the string. So you're going to increment I. And then you just do JL1 goes back. Do it again. Keep looping until you hit 0, which is the last character you just copied, is now terminated. And then it goes back to L2. In that case, you will restore S0, which you destroyed here, but you saved it before you destroy it. But before you go back, you have to restore it. And then you also restore stack pointer by 4, which you earlier you subtracted and just call JRR to return to the caller. So that's one way to translate that C code to this C code into this, which is perfectly valid, but may not be the best. It does showcases a couple of key points we were talking about. So this is just to say if a programmer has to load a 32-bit constant, we have the immediate version, the I version format of instructions where you can have 16-bit immediate. In many cases it's okay, but there are cases we're gonna need a number bigger than 16 bits. In that case, what do? You use load immediate into the high part of the RT register. So what they're doing is copy 16 bits constant, which is a 16 bits constant, to the left, which is the upper 16 bits of RT, and it clear the right side to be 0. So here's the example. 61 is a constant. If you look at the binary, it will look like this. That's 61. Just believe me. If you don't believe, go calculate. So if you do I made a mistake. So this should be LH high, loading high. So if you load this into S0, what happens is it will copy this content into the upper 16 bits, clear the lower 16 bits. Okay, so if you have a really big number, what you do next is you do a OR with the immediate number. By doing that, when you do a OR, the upper 16 is kept unchanged because it was 0, extended with 0 for the instance. But the lower one, because it was all 0 to start with, so basically whatever value you have is now set into this. So anyway, this particular example, if you really want to see it in the following example, really what we're trying to do is we're trying to set S0 to a very large 7 D0900. So this number is bigger than what 16-bit would be able to do. And we don't have any instructions, so what you do is you do is combination of 2 instructions to achieve the purpose. Okay, so now let's move on to another very useful instruction. So we have seen it in assembly code, but we never really know how does it work in the instruction. So this is the PC relative addressing, the things like BNE, B equal. How do they really jump? So here is how they do that. It's called using a PC relative addressing. The target address is current PC value. By the way, the PC value at this point is already +4. Remember, this is the instruction. After this instruction is fetched, PC is already added 4, so it's going to be next. So that new PC value is going to add to offset, which is this value, times 4. Again, the reason times 4 is because all instruction addresses has last 2 bits to be 0, so it's not useful to store them. Just discard them, give you more range. And this is a sign. I believe this is a sign, but we can always check the book. It's a sign integer, so you could both move PC forward, but if it's negative, you're moving PC backward. So let's look at another unconditional jump, J or JL. They just have different opcode, but their format is the same. So this is it's called a pseudo PC addressing. It's a little bit weird because what they're doing is PC. I wish I have a board I can draw. Basically, the top 4 bits. I would say, yeah, top 4 bits coming from PC. And then the bottom 28 bits, really 26 of them come from this, from this constant. And then last 2 bits is just 0. So I wish I should I really should draw a picture to show how the target address is consistent. Basically, I hope you can get a sense now. The top 6-bit comes from current PC, and the next 26-bit come from this constant, and the last 2 bits come from 0. And that will be the new address to PC, which is assigned to it. That's how they jump into it. So basically, what you can see is become a region. It forms a region with a size 256 megabytes. And this instruction allows you to jump to any address within that region. the current PC region. Yeah, I really should have a better picture for that. So here is a little bit of more examples to show how this would work. This is the earlier looping code, if you remember. I is in S3, K in S5, address in S6. So assuming the looping location is, 80,000 hex, what you're doing is these are memories, like 4 bytes increment, and those are the contents of the instruction. This represents the 3 register format, so-called R format, and this is the immediate format, and this is the just jump format. So, and those are the values of subfield. So shift to the left logical is 0 opcode, 0 function code, and then this just corresponds to the this is not used in shift case, and this corresponds to the register value of these 2 registers, and 4 here corresponds to the shift amount. It shouldn't be 4 actually, it should be 2. Amazing, there's so many mistakes in the book. This comes from the book. This really should be 2. So anyway, I'm not going to decode that. The most interesting one is this one. We saw this before, the loop, the simple loop. So we earlier we saw it as if T0 is not equal to T5, we're just going to jump to exit. Now, exactly what does that mean? It's using PC relative. So in this particular case, they put 2 there. The reason for 2 is because exit is 2 instructions below it. If you remember, in this case, it's going to be PC plus offset times 4. So it's going to be PC, which is this, plus offset, which is 2, times 4. So it's going to be 8. This number plus 8, what are you going to get? You get 80024. Sorry, this is not hex. This is not hex. Okay, this is just decimal. So 8 plus this gives this. That means when you're executing these instructions, and these 2 registers are not equal, PC will be set to this one. You will start to execute from that. That's equivalent to executing from this. And then also you see an unconditional jump from here. And what it's doing is it's just there's some bits manipulation again without seeing the detail. Basically the top 6 bits takes the PC, which is same as this, and then the next 24 bits come from this. And I really should check whether this will become this. But at this point, I just tend to believe that's the case. Oh, it is the case. The reason is because you're basically going to shift this 2 bits to the left, and that became this value. So here you're going to jump back. So this 2 examples shows how PC relative jump works, also shows how absolute jump works in detail. Let's see, what is the next one? Occasionally, the jump is too far for the 16-bit relative value to express. That is possible. You have a very long code, very long functions in scientific computation. So this is going to exceed this range. What's going to do? Compiler has a way of deal with it. So what they're doing is, instead of doing this, because you really can't do this, the distance between L1 is too far. So what you're going to do is, he's going to jump to L2, which is very close. you can imagine the difference is just the 1, the 4 bytes, because after execute, the PC will be here, the offset is just 1, and then move to this one. So basically, the changes equal to not equal. If not equal, you go this, and if it's equal, you jump to L1. Notice in this case, you have 26 bits plus 2 more, so you have 28 bits to express the range. And that's much larger than 16 bits. So by doing this, you can jump to a very far place. Oh, I already said it covers 28 bits. That is 256 megabytes region. Ooh, that's no good. Which is okay. I want to keep it look nice. Okay, so here's a summary of what's so-called all the addressing mode. Addressing is not just the address to the memory. Addressing means how instruction to get its operand, get its parameter. So we saw one way to do it is immediate. Basically, the operand is encoded in the instruction. For example, you do a add immediate with 100. So how do you get the second operand? That's encoded in the instruction. It's called immediate. And the other one is the R format. The content is embedded in the register. For example, in this case, in those two registers you have together. We already know. The next one is base register plus offset. We saw it in the load word case, or load byte and load half word case, where you have a base register and then you have an offset that became the address, and from that address you load the content into the register. So how do you get this operand in this case? It's called base addressing. And then we also saw PC relative addressing. For example, in BNE loop, if these two registers are not equal, you're going to jump -8. That means you're going to jump back. So in this case, -8 is relative to the PC value. That's called PC relative addressing. The last one is the jump. It's called a pseudo directed addressing. It's called a pseudo direct. If it's really direct, then this should be 32-bit. That's very direct. You can go anywhere in the whole memory. But it's not exactly. The top 6 bits are taken from the PC. So it's not direct. It's within the region you are direct. So it's called pseudo direct addressing. You need to understand all these 5 addressing modes. This is just a summary of what we learned before. Okay, so here is a summary of instruction encoding for the 3 instruction type: R type, immediate type, jump type. And here are the typical instructions: add, subdiv, and SSL, SLL. I type. Ooh. Oh yeah, LW, it is I type. So those are all I type, and there's a jump type. So this is the format. R type, you have 3 registers, you have a shipment amount, and those 2 defines opcode, and function type defines the instruction. I type is opcode defines it, and 2 register plus immediate. And jump case is 6-bit opcode address. So now we're going to move to, I think it's the last part of the lecture. Yeah. It's called a pseudo instructions. So most assembly instructions represents machine 1-to-1. You see, when you see add, you know there's a machine instruction add. When you see SLT, there's a SLT instruction. But sometimes some combination is used so often by programmer. assembler supports shortcut basically. For example, move. It's easy for people to remember. This means we move this into T0. But machine doesn't really have a move instruction. So assembler allows you to write this in code. In reality, it's just going to translate into this. It's going to add a 0 register to T1 and it stores into T0. Because 0 register is 0, this is effectively assigning the content of T1 to T0. There's another example. Earlier we talked about there's no branch on less than for efficiency reasons and for shorter clock cycle. But it happens so often. Assembler just says, go ahead and write this code, but I'm just going to translate it for you. So if programmer write BLT says if T0 less than T1, you can jump to L. Look, there's no such instruction. So when he sees this, he's going to translate it into if T0 less than T1, he's going to set 1 to AT. And then you compare whether AT is 0 or not. If AT is not 0, that means indeed that this is less than, and you jump to L. So it's basically achieving the same effect. But if it's not 0, it will continue to execute the next instruction, which is exactly what we want. So those are called pseudo instructions. Earlier we have seen an instruction called a no-op. Remember, every bit is 0, 0, 0, 0. So in some sense, that is also a pseudo instruction. Because if you look at the encoding, that really is an instruction doing a logical left shift of the 0 register from 0 register with 0 bits, which essentially does nothing. So that could be viewed as a pseudo instruction as well. I think we're just going to stop here because next is a good example, but I think it's best to be talked about in person. It's a little bit hairy. Yeah, so we're going to leave to the class when I come back. That's it for today. I'm really curious how much do you learn by watching the video, and again, just like a real class, watch out, it might be quiz down there. Okay, take care. See you next time in class.